All right, so in our last video for the week, before we go off to spring break and we ignore school for the entire spring break, here is the problem that I asked you to do, and it was challenging. I'm sure you were like, wow, this one was harder. So this is kind of like the epitome of what's going to happen for this. So the first thing I did, just to kind of highlight it, is I went ahead and looked at the u, making it the denominator as we have done in several of these rational functions. I got my du and then went ahead and factored out the 2. So I was looking at this idea that I needed to have an x plus 3 somewhere. And obviously I did not have an x plus 3 in the numerator because it was 3x minus 1. So then I started to manipulate it. And I wanted to add a form of 1 in there so that the net of what I added was 0. That was this plus 9 minus 9. Now you may ask, why did I do plus 9 and minus 9? Well, what I was trying to do was I was trying to get this x plus 3 somewhere in there. It didn't matter that the constant in front of it is not the 2 that I need, because that would be just a rider and I could pull it out. But I did need this x plus 3 in there to get it to match the du. So I went ahead and I did plus 9 so that I could factor the 3 out and get the x plus 3. And then, of course, I just combined these two last terms together to get this minus 10. And so that's what I did, is I took out the 3x minus 1 and replaced it with this algebraically equivalent numerator that was in a way better form of what I wanted to do. Then what I did is I split the integrand by pulling the rider out here to the front, right? So there's my rider pulled out. I pulled the rider that was a 10 from that constant out, and then I got it into the form that was the ones that are very similar to the 2 that I worked earlier. I was able to use a u substitution down here on the first term. In the second term, I completed the square and basically used an inverse trig integrand or antiderivative, and then I used the log antiderivative for the first one. So that's kind of the most challenging that I think that you can see, but kind of the point is that pretty much anytime you have a linear over a quadratic, you are going to be able to, in some way, split it out and use this u substitution with an inverse trig to help you out. Now, there is one more technique that we're going to do in this set of notes with these rational functions, and then I may mention one more that you will do in BC Calc or in Calc 2, but I won't explain that one. I'll just mention what it is. All right, so in this one, now we're looking at something a little different. So in all of the previous examples that we had so far, we had a degree on the denominator that was 1 larger than the degree on the numerator. Now notice on this one, it's the reverse. The numerator has a larger degree now. So our last, more advanced technique when you look at these rational functions is going to be that when you see that the degree on the top is more than the degree on the bottom, that you are going to perform polynomial division. And let's remind you of what we're doing with that. We kind of reviewed that at the beginning of the year. That anytime you're doing long division, we want to, I'm just going to jump down the numbers. You guys know how to do the numbers. I have a divisor that is x squared plus 0x plus 1. Okay, kind of put in the missing term. And then we have our x cubed minus 3x squared plus 0x plus 1. So notice that I'm putting in placeholders anywhere that there's a missing term. And so we're going to ask ourselves, now typically when you do these problems, you simply look at it, and there's not really enough, well, we can do it down here. So when I go to divide this in, what I'm going to do when I do the long division, and you might be asking, why aren't we using synthetic division here? But remember, synthetic division only works if you are dividing by a divisor of x plus a number, x minus a number. So we can't use it. So we're doing long division. The first thing you do is you ask yourself, how many times does x squared go into x cubed? Now, when we ask that, remember that when we are doing division, when I say how many times does x squared go into x cubed, I'm asking you to basically say what times x squared equals x cubed, and that would be x. We add that up to the top there. What we're going to do is we're going to then multiply, I'm going to do it in blue, this times each of these. And we're going to line them up underneath exactly where they have the degrees and the powers match up. It's kind of like putting it in the right place. So I'm going to have x cubed plus 0x squared plus 1x. And then if you'll recall from when you did long division in elementary school, we always subtract at this point coming down. These two terms should cancel, and if that doesn't happen, you've done something wrong. Then we have negative 3x squared minus 0, which is minus 3x squared. Then you have 0x minus 1x, so minus x. And then bring down the term that's still left here at the end, plus 1. Now we can keep going because our degrees are the same. So I ask myself now, how many times does x squared go into negative 3x squared? So negative 3x squared divided by x squared is negative 3. We add that to the top. We then multiply times each of the three terms in the divisor. So that would be minus 3x squared plus 0x and then minus 3. We are going to subtract and come down. And then when we subtract, these two should cancel. Negative x minus 0x is negative x. And 1 minus negative 3 is 1 plus 3 or plus 4. Then that means that when you go to rewrite it, that this fraction that we started with, okay, so I'm really just doing pre-calculus at this point. My x cubed minus 3x squared, x cubed minus 3x squared plus 1 divided by x squared plus 1 is equivalent to, it goes into it, x squared plus 1 divides into that polynomial, x minus 3 times plus your remainder. This is your remainder down here. It is your remainder because the degree is smaller than your divisor. The degree here is 1, whereas the degree up there is 2, so we know that that's the remainder, over your divisor, x squared plus 1. Now, once you get that, okay, so we have taken our improper rational function, we did polynomial division on it, we rewrote it as a polynomial plus a proper rational function, which just means that the degree on the bottom is larger than the top. And now we're essentially going to apply the techniques that we had. So we're going to integrate this x cubed minus 3x squared plus 1, x squared plus 1 dx. Instead, we're going to integrate the x minus 3 plus negative x plus 4 over x squared plus 1 dx. And I want you to pause the video and come back when you think you have this integrated and check with my key. All right, so let's check and see if you actually came out at the end of this, kind of getting the swing of things. So showing my work down here, all I had to do once we went through the polynomial division, the first part right here is simply linear, and we can integrate that fairly easily, so I separated that out. Then in the term that we had left, I went ahead and separated out the minus x over x squared plus 1 and the 4 over the x squared plus 1. And I went ahead and pulled the 4 to the front. So we knew that we had a u substitution for the middle term, and we had an inverse tangent for the last term. And we're done. So it turns what is a very challenging problem into something that is fairly easy. Now, I will tell you the last technique, there may be more than this in BC Calc, but the one that I do know, there is a technique called partial fractions. And partial fractions looks at this idea of if you have a fraction that has stuff here in the top and two factors in the bottom, like x minus 2x plus 3. Partial fractions is this idea that you can rewrite the fraction and do what I call uncommon denominator it, which is rewrite it as something over x minus 2 plus something over x plus 3, and to split it into two separate fractions that must have added together to give you this one fraction. And that splitting the fractions then would allow you to separate the integrands. But I'm not going to go over that because that's in BC Calc, and we'll save that for when you go back and take Calc 2 next year. All right, so our final thing here is I've given you several examples down here at the bottom. And what I would like you to do is to try them, if possible, using techniques from AB Calc. And if you don't think that any of the techniques that I have covered apply, tell me why. Okay? And I will put up a key to this. You can check that at the end, and that will finalize our material here before spring break. And again, just reminding you, I really want you guys to finish this up and then take a step away from school and spend some time with your family, play some games, go outside, walk your dog, but in all ways, just be safe, stay away, socialize, don't do any socializing, even with your friends. Let's work on our social distancing so that we can all come out of this quarantine and not be stuck in our houses anymore. So hopefully you guys have a great spring break. I will come back afterward and we will begin discussing reviewing and wrapping up from the AP lessons that are being posted on YouTube. So see you guys a week from now.